Welcome to the first in a series of videos on the topic of thermodynamics. These videos were developed primarily as an aid to undergraduate students studying the topic and hopefully will be of interest to others as well. First of all, what exactly is thermodynamics? The theory itself is defined in its very name. Thermo is the Greek word for heat, symbolized by the letter Q. Dynamics is motion, which can be turned into work, symbolized by the letter W. So thermodynamics is the study of energy flow, how heat can be converted into work, and work can be converted into heat. Primarily, it is a theory. It's a model to help people understand how the universe works. Therefore, it must be based upon very, very well-defined and precise parameters. For example, how is it being applied and where is it being applied? The boundaries of every problem must be clearly set out and explained in order for the explanation to make any sense. Similarly, within that definition, within that answer, words have definite meaning. Every term must be precisely defined so that the reader can understand what the conclusions are. And thirdly, the boundaries of the problem and the definitions of the terms used lead to limitations that also must be understood. These parameters must be clearly explained and clearly understood if the results of thermodynamics are to be applied usefully. The first term that's of importance is what is known as the system. Very simply and very grandly, the system is the part of the universe that is being studied. Under thermodynamics, systems come in four varieties. They may be, first of all, open, meaning that mass can enter or leave, and heat can enter or leave. An example of an open system would very simply be a pot on the stove. Mass can enter as you fill the pot with water. You can turn the stove on and add heat. As the water heats up, steam is developed and escapes, so the mass is now escaping the system. And if you happen to put your hand over the pot, you will find out that heat is also escaping. The second type of system is what's thermodynamically known as a closed system. In this case, mass can enter, but it may not leave, but heat can be exchanged with the surroundings. An example of this would be a pressure cooker. Once filled with water, mass can no longer go into the pressure cooker. Heat can be added, and you don't want to touch the system because heat is also lost as the entire pressure cooker gets hot. However, as the water is being converted into steam, no mass can be lost. The steam simply increases the pressure. Third type of system is an adiabatic system. This is the opposite of a closed system in that mass may enter or leave, but heat is trapped. Heat cannot get in or out. An example of this system is probably the simplest example, a styrofoam coffee cup. Mass can enter as you fill the cup with water or coffee. Mass can leave as you drink the coffee. But the entire purpose of the cup is to keep the coffee that's inside hot, while the cup itself and your hands remain cold. So you have an adiabatic system that you use pretty much every day. Type of system is also the rarest type of system, an isolated system. In an isolated system, mass cannot enter or leave, heat cannot enter or leave. In practice, the universe is the only isolated system Because since the universe by definition contains everything, there can be no surroundings to exchange mass or heat with. A second point that becomes very important in the study of thermodynamics, even though it seems simple, is the point of perspective. In thermodynamics, the sign of a change denotes the direction. Observations are made from the point of view of the system. This is not surprising because since we live in an isolated system, every observation we make is actually made from the point of view of being inside. So in this case, a positive change in either heat or work means that work or heat is added to the system. For example, when you compress a spring, as you push the spring down, you are adding potential energy to the system. You are adding to its ability to perform work in the future. A negative change is as work or heat are removed from the system. If you release that same spring, potential energy is being converted into kinetic energy, and less energy is therefore available to produce further work in the future. Third thing that must be kept in mind when studying thermodynamics is that the theory is based on the behavior of what are known as perfect gases. A perfect gas is similar to an ideal gas that you know from freshman chemistry, but also has even more limitations on it. As an ideal gas, it's filled with independently moving particles. The particles do not interact with each other, they do not attract, they do not repel, they will not react, and all collisions between them are totally elastic. The particles themselves occupy no significant volume, actually no volume at all theoretically, and the system obeys the ideal gas law, PV equals nRT, where N is the gas constant. In addition, for a perfect gas, the energy of the system is only dependent upon the amount of gas and the temperature. The energy of the system is independent of either the volume and or the pressure, which will be an important point that will come up slightly later on in these discussions. Thermodynamics studies systems. From the point of view of the system, where signs are either positive or negative, and that system has to be composed of a perfect gas. Fourthly, thermodynamics only studies things that are called state functions. A state function is a process whose result only depends on where the system started and where it ended. It only depends upon the difference between the variables defining the final state and the initial state. It is completely independent of the path taken. Okay. The system is described purely in terms of changing variables between the initial and the final state, and the number of variables that exist are actually quite limited. Even though you are discussing a universal model, it turns out, thermodynamically speaking, in the universe, there are only 5 variables. 4 of them are already known from the gas law: pressure, volume, temperature, and the amount of gas. The 5th variable comes from the definition of thermodynamics itself, and that would be heat. So what is a state function? Turns out potential energy is an example of a state function. Suppose there's a person who lives in the 3rd floor of a building, and that person, for some reason or other, wants to go outside. Maybe they want to get something to eat. Maybe they got to walk their dog. For some reason, they got to get out. There's 3 ways out of the building. First way, they could just walk down the stairs, walk down 1 flight, 2 flights, all 3 flights, however many it takes, and then they're outside. If they're lucky enough, they could live in a building with an elevator where all they have to do is walk down the hall, press a button, take a short ride, and outside they go. There is actually a 3rd way out of that 3rd floor window, which is not ideal or recommended, but you very simply could walk out the window. Each of these 3 cases involves different paths and significantly different outcomes. However, the potential energy of that person is the same regardless, because the potential energy only relies on the mass. So if we say our person is 100 kilograms, the acceleration due to gravity, and the height that they're traveling, so 10 meters for a 3-story building. So regardless of which path this person takes, 100 kilograms traveling 10 meters at 9.8 meters per second squared against gravity would have a change in potential energy of 9.8 kilojoules. That is a state function. You may notice out of the 3 pathways, walking down the stairs takes the most energy. Jumping out the window, although not recommended, takes the least energy. The amount of kinetic energy differs by the path taken. So kinetic energy is not a state function. So thermodynamics only deals with changes in state. The total energy of the system is never determined because it cannot be known. Thermodynamics is a universal study, where, as stated, the universe itself is the largest isolated system. It is impossible to know the total energy of the universe or any system, so therefore you can only determine changes. Those changes have to come in state functions, which only depend upon final minus initial, and are signified by the term delta. Other types of changes, such as kinetic energy, that depend upon the pathway taken, are called line integrals. These are denoted by the letter d, which may be familiar with from calculus, as in dy dx. Thirdly, and a new thing that complicates things a bit, changes of state can only be measured for a process which is reversible. Reversibility is going to be a major theme in the next several videos, as in what is it and how does one get around it? Because by definition, a reversible process is a process that occurs in an infinite number of steps, and each of those steps is infinitely small. In addition, each of those infinitely tiny steps is an equilibrium step, meaning it's one tiny step forward and one tiny step backwards. So essentially, a reversible process would take eternity to occur. Every single step would always be canceled out. Yet this is the only thing thermodynamics can answer. Future videos will get into how this is applied, how it's used, and how one gets around these limitations. And I hope you enjoy this video and move on to see other ones.